Hi, welcome back to educator.com. Today we're going to talk about midpoints, distance, the Pythagorean theorem, and slope. Got a bunch of things to talk about. The concepts in this lesson, like all the other introductory lessons, are all ideas you've seen in previous math classes. None of this should be totally new to you, but we definitely want to review them. There's important concepts for the course in here, right? We're going to be talking about this stuff later on. We're not going to directly talk about these other ideas. We're not going to be teaching on them directly, but other than this lesson where we'll be doing that directly, but it's going to be assumed that you understand them all. They're all going to repeatedly show up as we work on more complex things, so we really want to make sure all of these things are totally under our belt now and that we really get what we're doing. Not only that, but we really want to get what we're doing, right? We don't want to just be able to do these things. We want to understand how it works, how these formulas are operating. Not just how to use the formulas, but how they work, why they work, what they mean, what's causing them to be the way they are. As we get into more advanced math, like this course right here, it's going to become more and more important for you to understand the big picture, not just how you can do this one problem, but why doing the problem this way makes sense. As we see more and more complex ideas, it's absolutely necessary for you to be able to make sense of why we're doing the things we are. If you're just doing it because that's what you were told to and that was the step that has to come next, eventually things are going to fall apart and you're not going to be able to see what the next step is going to be. As you get older and older, you sort of take more responsibility on. As you get into more and more advanced subjects, you're expected to understand what's going on and be able to take things on yourself. You know, back in algebra, you were able to just take step-by-step formulas and apply them, but now you have to understand why those step-by-step formulas work, because you have to understand why that works so you can now tackle more complex ideas. So don't just understand how you can use this stuff, but understand what's going on a deeper level. That's what I really want you to get here, and what I want you to get out of the entire course at large. That should sort of be the goal of your education at this point, is being able to understand what it's doing, why it works, not just slogging through it so you can get the next grade. All right, let's get started. Let's say we wanted to find the point that's halfway between 0 and 4. That seems pretty easy, right? Halfway between 0 and 4, well, there's 0, there's okay. Click over, oh, hey, look, it's 2, right? It's just half of 4. 4 over 2 equals 2. But what if we wanted something a little bit more complex? Like we wanted to figure out the midpoint between -5 and 17. What point is halfway between those two? There's two ways we could approach this idea. Say we want to find the midpoint between -5 and 17. There's two ways to look at this question. First, we can look at it through the idea of distance. So the distance between -5 and 17, how far would we have to travel to get from -5 to 17? We'd have to travel 22, right? -5 to 0, we travel 5, 0 on to 17, we travel another 17. We can also look at it from the point of view of 17. 17 minus the guy before him, -5. We get 22 either way we do it. Technically, we haven't formally defined what distance means. We will in just a little bit, but this makes sense. We can see, yeah, that should be 22. So to find at the midpoint, what we can do is we'll start at -5, and then we'll work halfway up. We'll go up 22 over 2. So we start at -5, and then we add 22 over 2. 22 over 2 is 11, so -5 plus 11, we get 6. 6 is our answer. 6 is our midpoint. Let's look at another way to do it, though. What if instead we wanted to find it through the idea of a middle, right? We're looking for the midpoint, so it makes sense that the midpoint has to be halfway between them, right? What's going to be halfway between them will be the average of the two numbers. What would be if we combine those two and figure out what's the most common place you have between the two of you? What's going to be the middle between you two? It would be the average. So we take 17, we take -5, and we don't have to worry about the distance. We just realize, hey, look, midpoint's going to be halfway. To be halfway, you have to be the average of the two values. So we take -5 plus 17, and we divide it by 2. That gets us 12 over 2, which is 6. It's the exact same thing we figured out last time. That's great. It agrees with our previous work, and that's definitely what we want, right? Since both of these things made logical sense to us, they better both work, otherwise there's going to be a mistake somewhere in there. All right. At this point, we could maybe look at this in general, right? Let's say somebody hands us 2 points, A and B, and guarantees that A comes before B, that A is less than or equal to B. We've got this order that A will come before B or maybe on top of B. We don't know what they are, but we still want to be able to talk about the midpoint. From our previous work, we've got two ways to find this, right? The distance from A to B is going to be B minus A. So if we move up half of that distance, it's going to be B minus A over 2. So we'd start at A, and then we'd add b minus a over 2. That's our half of the distance idea. But we can also think, hey, look, I know I'm going to be here, and I know I'm here, so I'm looking for the place that's halfway between them, so we get the middle, that's a plus b over 2. Now, from what we saw before, we saw both of these ways work, as we'd hope. They give the same value, right? We can go with either a plus b minus a over 2, or a plus b over 2. They both do the same thing. Let's prove that they're actually equivalent, right? If we start off with our half distance formula right here, then we've got a plus b minus a over 2. Well, let's try to put them on the same fraction. So we make it 2a over 2. We can now combine fractions, so we get 2a plus b minus a over 2. At this point, 2a minus a, 2a minus a, we get a plus b over 2. So sure enough, our half distance is equal to our middle. They're just two different ways of saying the same thing. Since we have two ways to find the midpoint, and they're really just equivalent ways to get the same answer, we'll just, out of laziness, make one of them the official one, right? A good motivator to do anything is because it's the easier way. As opposed to having to memorize two different things or go with the slightly longer one, let's go with the slightly shorter one. So we make our midpoint formula a plus b over 2. There we are. Whatever the 2 points are that we're trying to find the middle between them, it's just a plus b over 2, because we're just looking for the mid place, and the mid place must be the average of our two locations. What if we want to do this in 2 dimensions, though? What if we wanted to find the midpoint between 0, 0 and 6, 2? Now, notice, we could look at this as opposed to trying to figure out what's the middle of the point, on a line that connects the two of them. I wish I had made that slightly more perfect. Instead of trying to figure out, well, what's the middle got to be here, we can go, well, hey, look, we know there's just going to be some distance vertical and some distance horizontal. It must be that it splits our distance halfway horizontally, and it splits our distance halfway vertically. So the two of them come together, and that's our midpoint. So it's going to have to be the horizontal middle. Our horizontal distance was 6, so 6 over 2 is where we're going. Our vertical distance was 2, so it's 2 divided by 2. So our location that's going to be halfway between them will be half of our horizontal distance and half of our vertical distance, 6 over 2, comma 2 over 2, or 3, comma 1. The midpoint is going to occur at the horizontal middle and the vertical middle put together into a single point. What if we were doing this for some arbitrary pair of points, x1, y1, and x2, y2? Well, same basic idea. We can think, what is the vertical and what is the horizontal? What is going to be the midpoints of those two things? We think with that idea, and we're able to come up with the same logic. It's going to occur at the horizontal and vertical middles, right? This point, it's going to be the same vertical height, because we never changed height as we went along. So horizontally, we're going to have changed to a new horizontal location, but vertically, this thing right here is going to be the same thing here. Same sort of idea here. Y2 is going to change when we switch down as we go down, but vertically, we didn't change it. Sorry, horizontally, I meant to say, not vertically. Horizontally, we didn't change there. So we've got fixed things here, so we're going, the point that we're meeting the two at, if we drop a perpendicular and throw out a horizontal, we're going to meet up at x2, comma y1. So the midpoint horizontally is going to be x2 minus x1, sorry, not x2 minus x1, x2 plus x1 divided by 2 will get us the middle location because it's the average of our two horizontal locations. The average of our two vertical locations is going to be y2 plus y1 over 2. We bring these two things together, and we get where our middle is. We get our midpoint that way. So from the midpoint in one dimension, we can figure out what it is horizontally. So horizontal motion was x1 plus x2. So its midpoint is x1 plus x2 over 2. And vertically, our motion was y1 and y2, or not our motion, our locations. Vertical locations were y1 and y2. So the middle of our vertical locations will be y1 plus y2 over 2. Great. So our midpoint formula is just x1 plus x2 over 2 and y1 plus y2 over 2. Awesome. Next idea, distance. What if we want to find the distance between 2 and 7? Easy. 7 minus 2 equals 5. Done, right? Well, we could make a mistake though, right? We're not perfect. What if we accidentally put it in the wrong order, right? We put in 2 minus 7 equals negative 5. Well, that doesn't really make sense because distance, it has to be a positive length, right? There's no such thing as a negative length. If we were measuring something, you can't say, oh yeah, that guy is -2 meters tall. It doesn't make sense. We can't say about his distance, his length as being -2. So -5 doesn't really work. But notice, 5 and -5, they're very different in one way, but in another way, they're very similar, right? One of them is the same thing, just with a negative sign. The other one is the same thing, but with a positive sign, right? So they're the same number, but with different signs on it, right? In one way, we can think of 5 and -5 as being very different numbers. They are opposites, after all. But another way, we can think of being the same number, but with different signs, right? They're the same distance from 0. So what we really want is we want some way of being able to force positiveness, right? 5 and -5, they're pretty close to both being the same thing. It's just one of them has the wrong sign. So if we could force it to be positive, it wouldn't matter if we did 7 - 2 or 2 - 7, because since we're forcing positive, it will always give us the same thing. We'd always find that distance, even if we put it in the wrong way. This is where the idea of absolute value comes in. We call this idea of forcing positive, making something always come out as positive, as absolute value. It's represented by vertical bars on either side. So whatever we want to take the absolute value of, we just put inside of 2 vertical bars. So we could have like x - 5, and whatever comes out after we plug in x, we would take its absolute value. We would force positiveness. It's going to take negatives and it will make them positive, and it will take positives and not do anything. Also, 0 won't do anything. If you're positive, you stay positive. If you're 0, you stay 0. If you're negative, you flip to being the positive version. You hit it with another negative. So -5 would become 5, but +5 would just become +5 as it already started. -47 would become 47. 47 would just stay as 47. Great. So with this idea of absolute value, we can now tackle how do we talk about distance in one dimension. So if we want to talk about it just arbitrary, if we have 2 points, some A and B, and we don't know who comes first, right? We don't know if it's going to be A, then B, or B, then A. We have no idea who comes first, if it's A first or B first. But we still want to be able to talk about what the distance is between them. Well, our previous logic would tell us that one of these two is going to be right, A minus B or B minus A. But the other one's going to be wrong, although almost correct, because it will be the negative version. So we've got A minus B versus B minus A. So what we want is we want some way of being able to say, well, let's just get rid of negative signs, right? Let's force everything to be positive. Then it doesn't matter what order we put it in, because it's going to be the same distance, because it's just a negative version or a positive version. It doesn't matter because we'll flip everything to positive. We'll always get the distance. So we toss some absolute values on there. Absolute value to the rescue. We wrap them in absolute values, and they both will become the same positive, correct distance. So the absolute value of A minus B is the same thing as the absolute value of B minus A, because the only difference would be whether or not it's negative or positive. I know they're both forced to be positive. So absolute value of A minus B is equal to the absolute value of B minus A, which is just going to be the distance between A and B, which is the distance between B and A. For ease, we'll just make the first one official. So the absolute value of A minus B is the distance between those two locations. We just take the absolute value of the difference, and that gives us how far two things are apart when it's in one dimension, when we're just on the number line. What if we're in more dimensions, though? Let's take a look at the Pythagorean theorem, as we'll need that to discuss 2 dimensions. So to discuss distance in 2 dimensions, we need to understand the Pythagorean theorem. You've probably learned this before. If it isn't really something that you know well, you're going to want to go back and relearn it. Make sure you've got this idea, because it's going to show up all sorts of places in pre-calculus and in calculus, and it's definitely going to show up a whole bunch in the trigonometry portion of this course. So definitely make sure you go restudy it if you don't remember it. What it was a right triangle. If we've got a right triangle, right angle in the corner, the square of the hypotenuse, that's the long side, the square of the hypotenuse, the side that is opposite our right angle, the square of the hypotenuse is equal to the sum of the squares of the other 2 legs. So we square each of the other 2 smaller legs, and when we add them together, A squared plus B squared, each of the smaller legs squared, then added together, that's going to be equal to our hypotenuse squared. A squared plus B squared equals C squared. Leg 1 squared plus leg 2 squared equals hypotenuse squared. That's the idea of the Pythagorean theorem. So anytime we see a right triangle showing up, anything we've got showing up in perpendiculars, it's a good idea to go, oh, I wonder if I could use the Pythagorean theorem here, as it will be very, very useful in a whole bunch of situations. If you aren't really comfortable with using it at this point, definitely go back, review this idea. Either search it up on the internet, just try to do a couple of exercises, make sure you're practiced up on it, or go review it on educator.com, listen to the lecture, and then practice some exercises. But you want to make sure you're definitely comfortable with the Pythagorean theorem, because it is going to show up a whole lot for the rest of the time you're doing math. All right, on to distance in 2 dimensions. So what if we wanted to find the distance between 0, 0 and 6, 8, right? Well, we can't just subtract and take absolute values because we've got 2 dimensions that we're running in, right? We've got to deal with both of these things at once. So what we do is we go, let's turn this into a triangle. We drop a perpendicular from 6, 8. We now have this right angle in the corner. And with this right angle in the corner, we can use the Pythagorean theorem. So when we did midpoint, we dropped down perpendiculars, we tossed out horizontals and perpendiculars, and we were able to get a right triangle going on, which allowed us to find middle locations for horizontal and vertical. Now we're allowing us to find horizontal lengths and vertical lengths. We break it into horizontal and vertical parts. So if we're at 6, 8 up here, then the distance that we traveled horizontally is 6. The distance that we traveled vertically is 8. Remember, 6 because that's the horizontal portion, 8 because that's the vertical portion. So we use the Pythagorean theorem. We know that d squared, the diagonal of the hypotenuse, is going to be equal to 6 squared plus 8 squared equals 36 plus 64 equals 100. So our diagonal, our distance, d equals 10. So we can figure out that this has got to be 10 up here on that side because we can turn it into a right triangle, which allows us to apply the Pythagorean theorem. What if we look at this in a more general way, where we just get 2 arbitrary points where we don't know what they are? It's x1, y1, our first point, and x2, y2. Now, we didn't talk about this explicitly the first time, but when I say x1, I'm not saying x times 1. I'm just saying our first x the first, y the first, x the second, y the second. That's what x1, y1, x2, y2. That's what you should interpret when you see those little subscripts, those little numbers bottom to the right. So x1, y1, x2, y2, they're just 2 arbitrary points sitting out in a plane. We can continue with this idea. We'll make a triangle. We'll toss out a horizontal from this one. We'll go straight with a horizontal out, and we'll drop directly down with a vertical, like this, and that will guarantee us that we've got a right triangle that we can now work with, and now we have a way of being able to talk about the distance of that. So we draw that in, and we can go, what's the horizontal length? Well, since we ended up at x2, right, because it's going to have the same horizontal location as our second point, we went from x1 to x2. Our distance is the absolute value of x2 minus x1. Horizontal length is going to be absolute value of x2 minus x1. What's the vertical length? What's the vertical leg of our triangle? Well, we end up at y2, and what's the location that we're starting on this triangle? It's going to be y1 because it's going to be the same as over here. So we go y2 minus y1, absolute value of that. That's going to be our vertical length. The length of the vertical leg of the triangle will be the absolute value of y2 minus y1. So if we want to know what the distance is, if we want to know what the diagonal is, it's going to be d squared equals the square of the absolute value of x2 minus x1 plus the square of y2 minus y1. So d squared equals absolute value of x2 minus x1 squared plus absolute value of y2 minus y1 squared. Now there's a little thing we can notice at this point. We can go, hey, if I have the absolute value of x2 minus x1 and then I square it, well, if I just take x2 minus x1 and I square that, that's going to be the same thing. Remember, if I have negative 7 squared, that comes out to be 49, which is the same thing as 7 squared. So we don't have to take an absolute value to begin with, because when it's the number times itself, if it has a negative, if it multiplies by itself with another negative, boom, those negatives are going to cancel each other out. But if we started positive, we're going to have no negatives anyway. So the absolute value of x2 minus x1 squared is equal to the quantity x2 minus x1 squared, because they're both going to come out to be positive in any case. So this is also the same for y, so we can actually drop our absolute values. We don't have to worry about absolute values when we're doing this, and the distance will be equal to the square root, because it's d squared equals this thing squared plus this thing squared, horizontal length squared plus vertical length squared. So d equals the square root, take the square root of both sides, so we get just d, square root of quantity x2 minus x1 squared plus y2 minus y1 squared. So the difference in our two horizontal locations squared plus the difference in our two vertical locations squared. Great, that's distance in 2 dimensions. All right, slope. Slope is a way to discuss how steep a line is, how quickly it's going up, how much it's changing one way or the other. So another way to interpret it is the rate of change, the rate that the line increases or decreases for every step to the right. So if we take one step over to the right, it tells us how much up we should go or how much down we should go, depending on if it's a positive slope or a negative slope. So one step over and we change by the slope. Either way we look at slope, whether we look at it as how steep it is, the angle we're working at, or if we look at it as the rate of change, how much we're changing for every step we take on the line, we define it the same way. We take some arbitrary portion of the line, any chunk of the line, and we see how much it rises and how much it runs. So rise is the vertical amount of change and run is the horizontal amount of change. So if we had some chunk of line like this, then what we do is we just set two arbitrary points here and here, and then we go, okay, how much did we move vertically? That's our run. And how much did we move horizontally? Oops, sorry, not our run. Said the wrong thing there. Our vertical change is our rise, right? Rise, you rise vertically. And our horizontal change is our run because you run along the ground, you run along generally horizontal things. So our rise compared to our run. We divide the rise by the run. So we symbolize it with m. Why do we symbolize it with m? Because clearly the first letter of slope starts with m, right? Makes sense. I'm kidding. There's actually no good reason and nobody knows why we use m. Go figure. Anyway, m equals rise over run. So that's how we symbolize it. The amount that we rised by divided by the amount that we ran. So we can also talk about this, since rise and run are just other words for vertical change and horizontal change. The slope is equal to the amount of vertical change in our line divided by the amount of horizontal change in our line. Now keep in mind, vertical change could go down, right? At which point we would have a negative negative rise. Keep accidentally swapping them. We would have a negative rise if we wound up dropping down. All right, why is it, let's go back for a real quick and address this asterisk. Why is it that we can look at any arbitrary portion of the line? Why doesn't it matter which section of the line we look at, right? Shouldn't it matter if we look at a big section or a small section, or if we look at a high section or a low section? No, because the line never changes slope. That's what it means to be a line. Every section of it is going along at the same steepness. Every section of it is going along at the same rate of change. If we put a bunch of sections together, they'll all agree on their slope. If we look at just one tiny section in a very different place, it's still going to have the same slope. Whatever part of the line we look at, it will always have the same slope, so we get the same value for slope no matter where we look on the line. So that's why we don't have to worry about what portion of the line we're considering. We just look somewhere, and that's our slope. Great. So if we have 2 points, they can define a line, right? 2 points define a line. So what do we want to find the slope between two arbitrary points, x1, y1, and x2, y2? Well, what we got to do is we got to go, all right, how much did I rise in that chunk? And I compare it to how much did I run in that chunk. We figure out both of those, and we'll be able to get what our slope has to be. So we build a right triangle to help us find these distances. Since this here is going to be the same as the horizontal of our second point, that matches up there, and it's going to be the same as the vertical, since vertical doesn't change as we go horizontally, those match up there. So the amount of run that we have is x2 minus x1. That's how much we changed as we went from left to right. And the amount vertically that we changed is y2 minus y1, because we went up from y1 to y2. We went up from y1 to some y2. So y2 minus y1. So our rise is y2 minus y1, and our run is x2 minus x1. Our slope is equal to the rise divided by the run, which is our vertical change divided by our horizontal change. So that gets us y2 minus y1 over x2 minus x1. We've been using this formula for years, but now hopefully you actually understood it before, but even if you didn't understand it before, why this formula was slope, hopefully now you're like, oh, now I see why slope is what it is because it's just coming from rise over run. That's how we defined it. So we get y2 minus y1 over x2 minus x1 because y2 minus y1 is how much we rose, and x2 minus x1 is how much we ran. Great. Being able to understand what we're doing with slope, though, requires being able to interpret it on an intuitive basis. We want to know what to immediately imagine when we are talking about something that has a slope of 50, right? So slope tells us how much the value of a line changes for every step to the right. If we have a slope of m equals 2, then that means if we take one step to the right, then we will go up 2 steps up. So our line will wind up looking like this, right? If we had a slope of, say, -3, then it would be for one step to the right, we take 3 steps down. So our line would look like that. Great. What we've got here is a way of being able to talk about the line's rate of change, how much you change for one click. You click over and you change by your slope. So we can think of slope as how steep it is, right? Bigger numbers will make it steeper because it means more steps to be made in our rate of change. Sorry, one step, but how many times we go down or how many times we go up is the number of our slope. So line's rate of change is its slope. It's a way of talking about how fast is this line changing as we slide along it. Want to keep these facts in mind as we think about slope. If we've got a positive slope, it means that the line is rising, and we're always thinking about it as we go from left to right. That's how we're always reading how our slope works. It's always what happens as we go from left to right. So positive slope means we rise as we go to the right. A negative slope means that we fall when we go to the right, right? We either go up by positive or we go down because it's negative. Bigger number, whether it's positive or it's negative, means a steeper line. The steeper the line is, the bigger the slope has to be. The bigger the slope is, the steeper the line is, right? A big slope, like say m equals 50, is going to be really, really super duper steep. It's going to go up really, really fast because for every step it takes to the right, it has to take 50 steps up. Similarly, an m equals -50, it's going to be very similar, but for every step it takes to the right, it takes 50 steps down, so it's super, super duper steep going down, right? So a big number, whether it's a big positive number or a big negative number, that's going to imply a steep line. Some specific locations to keep in mind: if m is equal to 1, then that means our line raises at a 45-degree angle, because for every step to the right, we take one step up, so it means that we've got a nice even-sided triangle, right? 45, these two have got to be the same here. If we've got m equals -1, then for every step we take over, we take a step down. So we've got same idea, but instead we're going down now. So these two angles have to be the same. We've got a nice 45-degree angle in that triangle as well, what makes up the line. So we're either rising at 45 degrees if we have a positive one, or we're falling at 45 degrees if we have a negative one. And if m equals 0, then we take one step over, we take no steps up. So we just continue taking steps over forever and ever. So m equals 0 means our line is horizontal. M equals 1 means our line rises at 45 degrees. M equals -1, line falls at 45 degrees. This also means that everything between 45 and -45, right? Everything between positive 45 and -45, that's all going to happen in fraction stuff that is between -1 and 1. If we want to get really steep stuff, that's as we approach either positive infinity or as we approach negative infinity. We can never be perfectly vertical with a slope because that would require infinity or either positive infinity or negative infinity, and we're not able to actually call those out because they're not really numbers. But as we go from 1 and click up more and more and more and approach infinity more and more and more, we'll need larger and larger numbers to become steeper and steeper and steeper. Great. All right. Lots of ideas that we've covered here. Now we're ready to start talking about some examples. First, the idea of midpoints. If we've got a midpoint and we're looking between -3 and 37, then our formula, remember our formula for midpoints was just a plus b over 2, right? It's the average of the two. So average of -3 and 37, put those two together, we get 34 over 2, which equals 17. So 17 is our answer. If we want to find 6, 2 to 1 comma negative 12, then we do it on each of the components because we look at the horizontal average, and we look at the vertical average. So 6 plus 1 over 2, the average of our horizontal components, and 2 plus negative 12, the average of our vertical components. So that will get us 7 over 2 and negative 10 over 2. 7 over 2, we can't simplify that anymore, but 7 over 2, so that'll lock in, but negative 10 over 2, we can simplify that, so we get negative 5. 7 over 2, comma, negative 5, that is our midpoint for this one right here. And our last one, what if somebody handed us things that weren't numbers, right? They hand us 2a, 3b, 6k, negative 7b. They are numbers in that a represents some number, right? It's a placeholder, it's a variable. B represents a number, k represents a number. They all represent numbers, but we can't actually solve and get numbers like we did with these previous two ideas, these previous two questions. But we can still use the numbers. We can still use the variables. We just put them into the formula just the same. We're still looking, what is the average of our horizontals? What is the average of 2a and 6k? What's the average of our horizontal locations? And what is the average of our vertical locations? 3b plus negative 7b. So we're still looking for the same sort of average ideas of horizontal and vertical. It just is, we can't combine 2a and 6k because a and k, they're speaking totally different languages. And b, we can combine because they're speaking the same language. So 2a plus 6k, can't combine that, but we can have our fraction, denominator, go on to both of them. So 2a over 2 plus 6k over 2, we have the denominator split onto both of them. And 3b plus negative 7b, that begins negative 4b over 2. So 2a over 2, that becomes just a. 6k over 2, that becomes 3k. Oh, whoops, not comma. They're combined together through addition, but they can't do anything more, right? A and k don't speak the same language, so they can't combine. But we've got a plus 3k. We know that's what our horizontal location is. So if we were given a and k later, we can easily get what the midpoint is in terms of actual numbers. Negative 4b over 2, that's negative 2b. There we are. We don't have numbers in the terms of like 53 or something, but we have answers that are still pretty darn good. If we get what these variables are later, if we somehow get them because we solve for them or somebody hands them to us, we'll be able to immediately find out what actual numbers would be. And this gives us a great idea of where the midpoint is based on variables. We don't have to be working with numbers to be able to solve for this stuff. We can also just put in variables and just follow the exact same rules that the numbers would follow. Next one, let's talk about distance. What is the distance between negative 7 and 8? Remember, we do this based off of the two numbers, the difference between the two numbers, absolute value. So we could go negative 7 minus 8 or absolute value of 8 minus negative 7. Either way we do this, negative 7 minus 8 will be negative 15. 8 minus negative 7 will be, turn those into positive 15. Either way, they both equal 15. So the answer is 15. The distance between negative 7 and 8 is 15, which makes sense because negative 7 clicks up to 0 by going 7, and 0 clicks up to 8 by going 8, so 7 plus 8, 15. Great, makes a lot of sense. What if we want to figure out what the distance is between 3, 7 and 9, negative 1? Well, remember, now we need to go, we're working off of what we figured out before with the Pythagorean theorem and how that applied to distance. So it's going to be the square root of the difference between our horizontals squared plus our difference between our verticals square root of all of that stuff. So formulaically, it is d equals square root of x2 minus x1 squared plus y2 minus y1 squared. Square root of all of that. So in this case, let's arbitrarily, we'll set this as our second guy and we'll set this as our first guy. So the distance is equal to the square root of x2 minus x1 squared, so that would be second x is 9 minus first x is 3 squared plus our y portion, second y is negative 1 minus first y is 7 squared. So distance is equal to the square root of 6 squared plus negative 8 squared. Distance equals 36 plus 64, which means the distance is equal to the square root of 100, which equals 10. So the distance between those 2 points is 10. Final one, what if we get some things that don't turn out nicely? We've got these ugly decimal numbers. We still follow the exact same idea. The distance is equal to the square root of arbitrarily, we'll just make this guy the first guy, this guy the second guy. The answer would turn out the same because of always the stuff we talked about before. It doesn't matter who gets turned into second, who gets turned into the first. The distance is going to be the same between them. If that doesn't really make sense, go back to when we talked about how we figured out this is the formula and notice that square root, that x2 minus x1 squared is the same thing as x1 minus x2 squared. It comes up with the ideas we were talking about absolute value before. So first x is negative 0.2 minus second x is 2.5 squared plus first y is 1 minus second y is 1.7 squared. So distance equals square root of negative 0.2 minus 2.5 becomes negative 2.7 squared, plus 1 minus 1.7 becomes negative 0.7 squared. We use a calculator to figure this out, or we could do it by hand, but I used a calculator when I figured it out, and I figured out before that negative 2.7 squared becomes 7.29, plus negative 0.7 squared becomes 0.49, because those negatives just wind up canceling with each other when they square against themselves. So 7.29 plus 0.49, so our distance is equal to the square root of 7.78, what we get when we combine these two numbers, 7.78. That's the distance between those two things. Of course, square root of 7.78, kind of hard to actually use if we had to, measure something and cut something. If we were making, say, a bookshelf, who knows? So we could approximate this. We could take the square root of 7.78 with our calculator, and that would be approximately equal to 2.79. In reality, the decimals actually keep going, and it keeps shifting around forever because 7.78, not a perfect square, so we can't just come up with a nice, easy number, but 2.79, blah, 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 blah. But we can just hack it off, and we'll say, yeah, 2.79, that's pretty good. So we get an approximate value. The true answer, though, is the square root of 7.78. That's what the answer really is. But if we need to be able to work with something that we can actually know what the number is pretty close to, because we're more concerned with having a sense of where it is than knowing precisely the right answer, then we could also get 2.79. Most teachers would probably accept both. Technically 7.78, the square root of 7.78, that's a better answer than 2.79 because we've lost a teensy bit of accuracy when we take the square root and then we round it. But we'll be able to use both. They're both very good answers. All right, next one. What would be the distance between the origin and 3, 12, 4? So we talked about stuff in 2 dimensions before. What if we have to deal with 3 dimensions, though? This problem is going to happen in 3 dimensions. So we talked briefly about 3-dimensional stuff before, where we've got 3 different axes, right? They're each perpendicular. So here's our x-axis, here's our y-axis, here's our z-axis. So here it goes x, y, z, like this. So if we were to plot this point, just to try to get a sense of what's going on, then we'd count out 3 on x, we'd count out 12 on y, and we'd count out 4 on z. So our point would be out 3, from 3 out to a distance of 12, and then from there up 4. Starting to accidentally encroach into my words, whoops. So our line is going to look like this. Now notice though, we could also think about a cross section here, right? This is getting a little complex to see. Let me see if I can get it a little bit more sensible with my hands. So imagine here's our x, here's our y, here's our z, right? So our number is going to go x forward, it's going to go y 12, and it's going to go up 4, right? Forward by 3. So we go out like this, right? We're going to start here, and we're going to go in all of these all at once. So we go out by 3, we go over by 12, and we go up by 4. So we could also think of this as being a cross section, right? We could take a cross section, and we could make a triangle in here, right? So we can say what happens in the xy plane, right? Here's x, here's y. So we go over 3, we go up 12, and we can talk about how we got here, right? We can do that portion of our trip We go travel x and y, then we go up. So we travel x and y, and we can figure out, well, hey, look, x and y plane is perpendicular to the z portion of our axis. So that's going to be perpendicular there as well. So we can figure out what this length here is, and then we already know what this is. It's got to be 4, because our height was 4. So if we could figure out what this portion right here is, what this length for our cross section, the base of our triangle is, we'd be good to go. So we look at the xy plane, we look at this portion here, and we can turn it into a nice flat object that we can see, a nice planar object. So we do the same stuff that we've been doing before. So here, 3 is our horizontal, 12 is our vertical, so our distance is going to be the square root of 12 squared plus 3 squared. Well, let's swap that around. That was exactly correct, but just to keep doing it the exact same way we have been doing it precisely before, we'll have 3 squared because we had horizontal before first, and then 12 squared because we were always following with vertical. The other way was just as right? 3 squared plus 12 squared is the same thing as 12 squared plus 3 squared after all, but that way we're just following our nice pattern from before. So we can figure out what the length of this portion right here is. So we have it right here. We now have that. Now we just bring in this thing and we just do another one. So d of our triangle here, let's use a different color. We'll go with green for the distance in our three-dimensional object. So in our three-dimensional object, it's going to be the square root of what it was in the xy plane, that distance squared. So what was it in the xy plane? It was the square root of 3 squared plus 12 squared. That was its distance before, but we have to square it, plus what was the jump that it had up? What was its vertical leap in the z? That was 4, so plus 4 squared. Now notice, when we take a square root and square it, like we've got in here, d equals, so square root of 3 squared plus 12 squared is just going to crack it open, and we'll get 3 squared plus 12 squared, and then plus 4 squared. We simplify this, and we get d equals square root of 9 plus 144 plus 16. Simplify that some more. We get square root of 169, which equals 13. So our distance is 13. So what we've done is we're able to look at how did it change on the first plane. We sort of take a cut so that we can look at how did it change in the xy plane, and then we toss on the z. Now, you might be getting a sense of, oh, hey, maybe there's something we could do in general. And I didn't tell you this before because it's not really going to come up much in this course. But we can actually get a distance for 3 dimensions as well. It's going to be distance of square root of a whole bunch of stuff now, of x2 minus x1 squared, the square in our horizontal, plus y2 minus y1 squared, square in our vertical, plus z2 minus z1 squared, square in our coming out of the xy plane. That comes out because what we do is we figure out the xy plane first. It's going to have a square root around it, right? But then when we toss on that z, when we toss out that coming out perpendicularly, we're going to square it again because now we're doing another right triangle, and so it will simplify to just each one of these differences squared. This might be a slightly complex idea for you, so don't worry if this didn't make sense. Just take it out of your head, throw it away. It's not really going to come up. It's just a really cool thing that if you're like, oh, hey, there's something interesting going on here, you're right. This is the interesting that's going on. We can actually generalize this to 3 dimensions, and if we wanted, we could even keep going to 4, 5, 6, any number of dimensions we want, and you might have some idea of what's going to happen as we go on to 4 dimensions. See if you can figure out what goes on in 4 dimensions. It's kind of cool. All right, example 4, what's the slope between -1, 8 and 1, 14? So remember, we figured out slope is rise over run. So the amount that we rise is our change in our vertical, so y2 minus y1, our 2 vertical locations, the change, and our run is our 2 horizontal locations, their change. So in this case, arbitrarily, let's make this guy the second guy and this guy the first guy. No particular reason, just because, that guy came first, that guy came second. So let's look at it that way. It also makes sense because if we were to draw a picture of it, we'd have something like this, -1, 8, and then 1, 14. So it makes sense to think of this guy as the second guy and this guy as the first guy. But as we'll see in a little bit, it actually doesn't matter which one we choose first. So the slope is -1, we want to find out the slope between -1, 8 and 1, 14. So then m equals y2 minus y1 over x2 minus x1. So our second y is 14, so 14 minus our first y is 8, divided by our second x is 1, our first x is -1, so minus -1, equals 6. 1 minus -1, those negatives cancel. We get 6 over 2 equals 3. So our slope is 3. What is the slope going to be if we switch our first and second points, right? So instead, we make this guy 1 and we make this guy 2. Well, we do the same thing. M equals, so it's going to be our new second guy is 8 minus our new first guy is 14 divided by x2, our new second guy is -1 minus our new first guy is 1. 8 minus 14, -6. -1 minus 1, -2. Hey, will you look at that? These cancel and we get the exact same thing. So if we switch our first and second points, who we arbitrarily decided to make second and first, does it affect what the slope comes out to be? No, it doesn't. Why? Because the negatives, it introduces negatives on both the top and the bottom. They cancel out. So if we have negatives showing up because of the switch, they're going to show up on both the top and the bottom, so we'll always see cancellation. So it doesn't matter if we plug in our one guy as the first guy or if we plug in that guy as the second guy. It doesn't matter who gets to be called first and second as long as we match up our seconds and our firsts have to match up vertically. If we have one point be the second point on the top, the second y coordinate, then has to also be the second x coordinate, has to come first on the bottom as well. So minus, we have to make sure that the points match up vertically, right? 8 and -1, -1, comma 8, 14 and 1, 1, comma 14. They match up there. Let's prove this though. If we want to prove that this always comes out to be the case. So to prove this, what we want to show is that it doesn't matter if it's y2 minus y1 over x2 minus x1 versus y1 minus y2 over x1 minus x2, right? If we swap the location of who gets to come first, who gets to be more on the left in the fraction. It doesn't matter who gets to be more on the left or who's more on the right. That's what we want to show. So how do we prove it? Well, let's start off with this guy here. So we'll have y2 minus y1 over x2 minus x1. Now, we want to be able to get that to start looking like this thing. And we say, well, y2 minus y1, oh, hey, that's pretty much the same thing, but it's got a negative introduced to it, right? So how could we introduce some negatives here? Well, let's write it again, y2 minus y1 over x2 minus x1. We can multiply it by 1, right? Wait, what? Well, yeah, 1, right? I can multiply anything by 1 anytime I want. You can't stop me from multiplying by 1, right? I can take any number and multiply it by 1, and it has no effect. So everything is equal to just itself times 1. Now, the cool thing about math is there's a lot of ways to say the number 1, right? I can say 1 as 1, but I could also say it as 1 over 1. Or I could say it as 5 over 5. Or I could say it as -1 over -1. And that's how we introduce our negatives, right? And this is also the idea that's coming along when we change denominators, is we introduce by multiplying the same thing on the top and the bottom. So we multiplied by -1 on the top and -1 on the bottom. Now notice, since we're multiplying the top, we're not just multiplying the first part of the top, we're multiplying the whole top. So because it's multiplication, it's going to apply to this fraction as if it started in parentheses. So times -1 over -1, y2 minus y1 times -1 becomes -y2 plus y1 over -x2 plus x1. And hey, this thing right here is just the exact same thing as this thing right here. We've just swapped the location. It's now, instead of -y2 plus y1, it becomes y1 minus y2, what we're a little more used to seeing. Cool. So we managed to prove that it doesn't matter what order we slot it into using this y2 minus y1 over x2 minus x1 formula. It doesn't matter because it's going to wind up spitting out the same answers. But the really key idea to think about when we're talking about slope is it is the rise over the run. It is the rate of change, how quickly the line is changing. All right, hope you learned a bunch here. Hope it's been a great refresher and everything's really clicking into place because we'll be using this stuff a whole bunch later down the road. All right, see you at educator.com later. Bye.